Okay, good morning, afternoon, or evening, everybody. Welcome to the Accelerating Scientific Discovery through Exploratory and Open Data Access via OPeNDAP and the Cloud ESDIS Data Training webinar. This is your host, Jennifer Brennan. It is 2 p.m. Eastern Daylight Saving Time, and so we're going to go ahead and get started here. What I'd like to do first is begin today's webinar with a few logistics. To ensure the best audio experience, all participants have been placed in silent mode, but if you have any issues or you have any questions, please enter those into the Q&A panel rather than the chat, and you should see that on the right side of your screen. If you don't see it, you can click on the 3 dots at the bottom of your screen to pull up your panel options, and then you'll insert a check mark next to the Q&A. Okay, today's webinar is being recorded. The recording will be posted to our NASA Earthdata YouTube channel within a week of completion. And then once completed, what I will do is I'll send an email to all registrants and participants that includes links to both the recording and presentation slide deck used within today's webinar. As far as timing is concerned, today's event will be 1 hour long with 45 minutes allocated to the presentation and live demonstrations, and a 15-minute question and answer period to begin after the presentation. Depending on the volume of questions that we receive, we may extend, and also depending on when we end the event, we may extend the Q&A session, but we will have a hard cutoff of 3:15 p.m. Eastern Time. During today's webinar, we will have 1 speaker and 1 Q&A panelist. Let me advance my slides here. Our speaker this afternoon is Dr. Miguel Jimenez Urias. Miguel is the computational oceanographer and also science community director for OPeNDAP. Our Q&A panelist this afternoon is James Gallagher. James is the president and also principal software engineer for OPeNDAP. What I'd like to do next is move to this afternoon's agenda. Our speaker will begin today's webinar with an introduction to OPeNDAP and OPeNDAP in the cloud. And then from there, we will transition to a series of data access demonstrations, which include requirements and where to find the interactive binder used within today's demonstrations, how to use Earthdata Search to find OPeNDAP cloud URLs, and also how to use Hyrax in the cloud. And then from there, we're going to transition to a series of Python-based Jupyter notebooks that show you how to access OPeNDAP data in the cloud, find OPeNDAP cloud URLs, and then work with both Xarray and Pydap to aggregate multiple OPeNDAP URLs to create a virtual data cube, and earthaccess to create a virtual Xarray data cube using DMR++ in the cloud. After Miguel has finished with his presentation and his demonstrations, he's going to toss it back over to me for the final optional polling questions, and then we'll just transition directly into the Q&A session. We'll try to answer all the questions within the time allotted, but if we are not able to address your question during the Q&A period, our speakers will be able to follow up with you offline. With that, it is my pleasure to introduce today's speaker, Dr. Miguel Jimenez Urias. Miguel, I'm going to stop sharing my screen at this point, and then I'm going to toss it over to you, okay? So let me do that. Alrighty, and then Miguel, you should have presenter privileges.
All right. Are you able to see my screen, my presentation slides?
I can. Yes, thank you so much.
Okay, great. Just to confirm, well, thank you very much. Everybody, I'm very happy to be here. James and I myself are very happy to be here, very excited to share some of the work that OPeNDAP has been doing essentially over the last 10 years. I think we checked, and the last webinar for OPeNDAP was 10 years ago, so I'm very excited to be here. I know James is also the team of OPeNDAP. We're really excited that we are sharing what we're doing right now with you guys. And thank you again for showing up to this webinar. I know it's being recorded. These presentation slides, you're already uploaded towards the Nodo community. You can find it on our OPeNDAP website under presentations. If you are interested in learning more about this, there's a lot of the content here that's already there. Follow the slides. I know that Jennifer already showed the agenda. I just wanted to show a little bit because one of great things that is, I feel like about OpenDAP, there's very different levels of expertise that requires to really know how to do OpenDAP well. And well, it's maybe an asterisk there, but I feel like I wanted to show this again, just to talk a bit briefly that it will require your Earthdata logging, an active account, Earthdata logging, username, password, particularly for using earthaccess, but especially we'll be using tokens. I'll go through that again. But one of the reasons I wanted to show this is because I didn't do that, but I could also draw like a vertical line an arrow pointing down in terms of the level of expertise that it requires. So one of the fun things and I fun challenge for this webinar is just to, without knowing who's going to be here to learn about OpenDAP and their own levels of expertise, kind of to cover all the different levels of expertise, starting from the traditional web browser approach of using OpenDAP. I think it will be beneficial for everybody here to kind of understand all the different levels of it. And with that, I'll just keep going. This isn't a lecture, but I figured that it would be really nice to talk a little bit about OpenDAP and OpenDAP's role within the NASA ecosystem, and kind of address also maybe some people who might not be familiar with OpenDAP about what is OpenDAP even. And so a bit about starting first about the job or the role that OpenDAP is doing within the NASA ecosystem is really to address NASA's data challenges. NASA data tends to be hierarchical. Not all of it is really nice level 4 data, which is model output, or level 3 data. A lot of it is hierarchical, many different types, many different variables, length size, chunk sizes, different levels of processing, different file formats, HDF5, NetCDF, NetCDF4, HDF4 EOS. Data is heterogeneous, hierarchical, and a lot of it's growing at a pace that it's really, really amazing to see the amounts of volumes of data that are being generated. A lot of it being migrated to the cloud, and that's the role that OpenDAP plays in the cloud. But not all of the NASA data it's on the cloud, and so OpenDAP also plays some roles on premises. And so we'll probably skip all of that in terms of on-premises services, but they're very similar. What is OpenDAP? Let's just start maybe with there. So it's OpenDAP stands for Open Source Project for a Network Data Access Protocol. It was designed jointly by scientists, software developers, system architects, essentially to share data without actually sharing the data itself, the physical file itself. Back then in the late 90s, it was designed to be open source. And so people would have a URL that pointed to a data set somewhere. And so scientists will, rather than sending each other the physical file, they would just share the URL, which I found it was a really neat idea that's still being widely used today. And it was also designed so that whenever the user had the URL, would be able to subset the data in a way that is data proximate, meaning that you don't have to download the entire file to only extract the variable or the chunk of the variable that you need. And those are the ideas that are still percolate today, and they're so relevant when we moved from late 90s to early 2000s, from gigabytes of data to potentially terabytes and terabytes and potentially petabytes of data. It was designed to be discipline neutral, of course, and interoperable. I know I'm going to be leaning heavily on the Python tools, but we're also aware that people can access OpenDAP URLs and OpenDAP data via other applications, like MATLAB, for example, is a huge supporter. And so we have this little diagram of some of the tools that people can use whenever they're running their compute environment, whether it's remote on some sort of EC2 instance. When we say cloud, sometimes I often refer to an EC2 instance, but also, ironically, cloud can also be storage. So it's these two things. But you can run your computer somewhere else or locally, and then the way that people interact with OpenDAP is kind of seamless, independent where you run this computer environment. So in the case of the cloud, then you have a URL, and then your program is able to add constraint. We call them constraint expressions, which is where the subset comes from. If a URL is an entire data set, then a URL plus constraint expressions essentially mean that you're subsetting in a way that is data proximate. And it relevant to OpenDAP is that users may hear about different types of OpenDAP. In this case, OpenDAP really will refer to the data server called Hyrax which is the one we actively maintain by our organization. So it's the Hyrax data server that runs in the cloud. So whenever I say OPeNDAP in the cloud, I really am referring to Hyrax in the cloud, just to be a little bit more specific. And if you want to learn more about Hyrax data server, you're welcome to come to our reference right here at the bottom left for all learning more about interoperability or data types that the data server is able to do. I swear this is not a lecture. I just have 2 more slides and that's it. We can play with data. Another thing about OPeNDAP is that there's 2 really broad protocols. There's 2 specific protocols that people can use to exploit OPeNDAP services. Hyrax implements 2 types, DAP4, which is the really newer the DAP protocol. It's newer and it's also more broad. It covers most, if not all, of the NASA data types that are available on the cloud. That may be arrays, that may be hierarchical data set like groups, types, data types, atomic types, containers, and it's backward compatible. Even though grids was kind of left in the DAP2 protocol, if you are able to, a grid can be accessed through a DAP4 protocol. It would just not be called a grid. It will be just called simple. So if DAP4 is broader in scope, a little bit more complicated, but it's broader in scope and it's backward compatible. So if you are able to open something with DAP2, then you're able to open it with DAP4. And then OPeNDAP is really one of the great things about OPeNDAP is that these DAP protocols implement metadata conventions that are really standardized and so allowed to share data across programs in a way that it's just always the same information representation. And so the entire webinar, I'm just going to refer to DAP4. And I'm going to show when we go to the demonstrations of how you can specify not to Hyrax data server, but to the client programs that you're using in Python tools, how to access DAP4 data, because that will be relevant. For example, when people talk about groups or other data representations. And it's also more performant. DAP4 is newer and it has better support for checksums. And the last slide, I swear, is this whole idea about the really, really excited that it's being widely adopted by the community of what we call the DMR++. This is a metadata representation of what's inside the file with extra information. And this is something that's specific to our OPeNDAP server called Hyrax. So Hyrax is able to produce this on the fly. When you have data on the cloud, this is what we call the DMR-PP or DMR++ file, which is just essentially the same metadata representation, which is CF compliant, but it also covers this plus pack, which part, this PP part, which contains chunk references, chunk information like compression, byte, offset. And you can think of it really as a map. It's a file that is just metadata that tells a Hyrax or a program is able to understand this metadata, what's inside the file without actually opening the file. And people who are aware with cloud access is that opening a file, especially if it's hierarchical, can actually have a penalty in terms of performance. So rather than if you have a collection that may cover hundreds of files, say HDF5 across and within the same bucket, rather than opening 100 files to figure what's inside and all of this chunky representation, you just read the metadata. So that is something that we're really excited about. In terms of NASA, this DMRPP sit right next to the file that they point to, the reference on the same bucket on S3. That's not necessary, but that's usually the case that NASA implements. And it's all open source. If you really want to learn more about DMR++, you can go again to the documentation on our website. And this is the last slide. Essentially, it's a lot of packing information, but essentially kind of how to open up in the cloud, I call it. One way to do it is that, well, first we need some cloud OPeNDAP URLs. And what does a cloud OPeNDAP URL looks like? Well, it's at the bottom left. That's exactly what a cloud OPeNDAP URL looks like. If you have an OPeNDAP URL that doesn't begin with opendap.earthdata.nasa.gov, it's not a cloud OPeNDAP URL. So that's a very distinct information. And that also means that there will not be a DMR++ associated with it. There's an equivalence there when you have a cloud OPeNDAP URL to whether there's a DMR++ available for cloud access in a way that is optimal. So whenever I'm talking about cloud OPeNDAP URL or cloud Hyrax URL, I'm really talking about a URL that looks like that. And we're going to use that. We're going to find them there in our interactive demonstrations. And so the way they work within the NASA ecosystem, that you usually have a collection concept ID associated with a collection, which may have spanned hundreds, potentially thousands of URLs or datasets, one per dataset, one URL per dataset. And then you want to find all of the granules in order to build this data cube. And so you will use some potentially some Python tools or some web browser tools, and that's what we're going to find. You will need to be authenticated. EDL authentication is necessary. There's different ways to authenticate, and we'll cover that, particularly with username, password. And then again, Hyrax uses DMR++ for efficient access in a way that the user doesn't actually have to care about. They may not be even aware that there's something happening, and that's probably the best way to do it, to leave the job for the software so that people don't have to care about it. They don't have to care what type of file format it is. They just want to access data in a way that is performant. And lastly, when you're running in the cloud versus an on-premise services, what's very specific about it, and this has to do with DMR++, is that you're able to specify the download type options. There can only be netcdf4, netcdf3, binary DAP, which is a type of binary that is very nice to stream over the cloud or over HTTP requests, or CSV. And that's very different, because if you have an on-premise services server like a Hyrax data server running on premises, some DACs do, you can specify more different types of file formats to which to download from. But when you're running in the cloud, when you cloud OPeNDAP URL, because it uses DMR++, then you're able to kind of select these three. Maybe netcdf3 as well, but we recommend netcdf4 because it's a broader in scope. And the one last thing I want to say about is that in terms of the interactive part of it, which is the demonstration, is that we'll use earthaccess, which can be run on the cloud directly, and it has their own form of authentication. And then they would access the files directly, but they will use metadata information, DMRPP, as opposed to using Pydap, which actually talks to the server directly, that's running in the cloud, and it downloads data as a DAP response and then reconstructs the file itself. So those are kind of two really interesting, I think, complementary ways to talking to data in the cloud. With earthaccess, we just access directly on the cloud, and so it can be very performant if you have the capacity to run data or just compute power on an EC2 instance. That gives you a huge boost. People like myself, maybe we don't have a lot of credits, so you can also use Pydap, and you'll still be using a pattern that is cloud performant via directly Hyrax. And the difference between the two of them is that you're getting DAB responses, which are very streamable. And with that in mind, we can move on to some of the demonstrations. The figure is still the same, but I just want a bit overview what I'm going to do. First thing, requirements is authentication, EDL authentication. So please be sure, I'm going to leave this for a minute here. Just be sure to be authenticated. You can just go to that website at the bottom left. It's a requirement there, and just log in. We'll use username, password. When you use the browser, which is a traditional OPeNDAP approach to finding URLs, as long as your browser has been authenticated, it'll be fine. But for something more interactive, like running a Jupyter binder environment, you will need to have your authentication handy, like username, password. We'll use tokens for Pydap, which is it avoids some redirects, not all of them, but it gives you a little bit of a boost there. And so the first thing we're going to do, and I'm going to leave this maybe for another minute, is that just to wait so that making sure the people are authenticated with the browser. You can just go here, and if you're not, just create this free account that you can create. I'm assuming because people are here for the Earthdata webinar that they are, but I'm just going to wait for another maybe 30 seconds. The first thing I'm going to do is go to the traditional web browser approach. Even though this is a Hyrax that runs in the cloud, the field should be the same. The only thing that might be different from the user will be the format of that URL string, which will be like Earthdata, OPeNDAP at .earthdata and everything. So this is where we're going to start search, and we're going to search for, let's say, eco-stress data product, which is level 2 data. It has groups in them. And so we're just going to demonstrate how to go to search data portal and then find data and find one single OPeNDAP URL. We're going to open that and then maybe inspect what's inside, look at the metadata again, because Hyrax gives you a view of the metadata. then you're able to kind of only download the bits of information that you want. So you can subset in space or potentially in time if you have a URL that covers time, or just you can do the graphical interface. For the next part, and I'm going to ask people to go to this here. This is where the binder is. I'm going to go through this. I'm just going to make sure that at least you go to this URL, and then I'm gonna show how to open the binder, and it's gonna run some Jupyter notebooks for running Python on. It's not gonna be an EC2 instance, but if you will have the credits to run this in an EC2 instance, you can. And just run it. I'm gonna run it on the binder environment. So with that in mind, I'm gonna go to the browser experience, which is that search portal. And I'm just gonna share now my browser. And I apologize for all of this logistics. Let's see what else. I'm just going to share my screen so that our people are able to see what I'm doing. And so I'm hoping that you're able to see my screen. As the only tab that is open right now is this. And this is a great way, interactive way to find data on the cloud. I'm just going to move the map. Oh, it went really small here. Here it is. It has sometimes double clicking. So I'm going to look for eco-stress data. Looks like I am. There it is. Perfect. So let's search for eco-stress data. Okay. This is going to be level 2 data. It's a product. So I'm just going to type eco-stress. And then the key here is that there's 2 types of file formats that they offer. We're going to pick the regional file format, HDF. We want to make sure that people building their own applications can actually have a chance to work with the original data itself. And we're also going to make sure that it's their Earthdata on the cloud. So this is perfect. So this is SWAT data, level 2 data, hierarchical, and then it's land surface temperature. So we're going to click on this collection. It has lots of granules, and I'm going to apply a filter. Let's just do a rectangle. I'm in sunny Pacific Northwest. So I'm kind of interested in regions, SWATs that cover this area. And so just by doing that, and just a spatial subsetting, I'm not really going to do temporal. I'm kind of interested to see how many. Oh, actually, here it is. It found almost 10,000 granules, which is great. That means there's potentially 10,000 OPeNDAP URLs. That's maybe a little too much for our browser experience to get all of those. The one way to, let's say, I'm going to select one of them that's maybe off the coast of California. And the way to find OPeNDAP URLs, there's different ways to do it. But this is actually going to tie to what I'm going to demonstrate with Python tools, is that you go into the information for that granule. Sometimes you can go to all these other related URLs, but I'm just going to do find, and I'm going to do OPeNDAP. And there it is. So here, this particular granule, a granule you can think of as a file, and you see it's cloud OPeNDAP. So I can actually just do copy, get a new tab, and then paste it, and it should take you to OPeNDAP's or Hyrax DAP4 data request form if my internet works fine. Okay, so here it is. It's a very traditional approach. What's here? It has a lot of information metadata. It has groups, hierarchical data. It's quite complicated. And so even just parsing this data set may not be very performant when running Python tools. I know that you can open some groups directly, especially in this case, particularly parsing DMR++ can take some time. And I'm only interested in this case. I'm just going to demonstrate something, the simplest thing that I can do right now. I guess we're building the level of expertise right now, is to just get a single variable. It tells you the size of it, 5,000 per dimensions. I'm just going to get maybe the first 100 bits of it. So then what I'm doing, essentially telling Hyrax, which is running in the cloud and is aware of the DMR++ and the chunk sizes and the compression, is that I only want this variable, one single variable for this granule, and I'm going to download it as netcdf4. And so there's a attention key warning, because if you want to download it, say as maybe netcdf3, then it may give you trouble because it has groups in it. And so I click download data. It should take some time. It has to go through some redirection authentication, and then it download into my machine. So great. That's one way to do it. You got one, you open that URL, you found one, Maybe that's not the most performant way to do it, but this is a very easy way to find OPeNDAP URL, especially when you're doing exploratory data analysis, to inspect what the metadata inside of a file is and just to discern or identify what you want and what you don't want. And then you can specify, you can construct these constraint expressions yourself. And so that's what we're going to demonstrate. So I'm going to go now to the GitHub repository for OPeNDAP. This is the official OPeNDAP GitHub repository. And so this is the URL that I want to show. I mentioned before. So this is has a binder environment that I'm going to leave there for maybe it's more 10 more seconds in case people want to look at it. I'm hoping that you're able to see the URL. I know this is being recorded, so people might be able to look at this later at a different time. So with that in mind, I'm just going to click on the binder and just open in a different tab, actually. Might be easier. And so I'm going to kind of reproduce this workflow of getting an environment and then finding cloud OPeNDAP URLs, potentially now hundreds of them, and then create a virtual aggregated representation with Xarray, which uses parallelization under the hood with Dask. So I'm going to do two things, like I mentioned. First, with Pydap as an engine. Here at OPeNDAP, we are working to maintain and develop and improve the features of Pydap to make it more performant. And also, we're going to demonstrate with earthaccess, which is this amazing community-driven package within the NASA ecosystem, or really is more community-driven. That is really exploiting OPeNDAP tools, and particularly DMR++ directly. So the first thing to do within this binder environment, and I think I'm running good with time, is to run this notebook, which is called Get Started. This is essentially what it does, is that it makes you to get your login credentials for and like your EDL. And in particularly when running Pydap, we're going to use the token. I know that most people, when you create a free account, they might not come with token, or sometimes they expire. I forget how often they expire. Like this one clearly is an older one. I generate a new one, I promise. So you'll need to do that and then just copy paste. So that's what I'm going to do here. So feel free to follow me along. If you can, that'll be great, especially when you have questions. But I'm going to demonstrate a lot of this and I'm going to talk through it. And please, if you have questions, write them in the chat. James is there and he can answer some pointed questions. And so in this case, I'm going to get my token. Let's see if it opened. I can't see my tab. Oh yeah, it did. So I'm going to get my token. And so let's see, I'm not going to show anything. I'm just going to get the token directly. And what I'm going to do is it's going to ask for it, Shift Command, and then hit return. And so now what I'm going to do for this binder, specific to this binder, is just to store my token on this this little environment so that it can be used across different sessions. And it's not a persistent thing, it's just for myself. There's different approaches to authenticate. For example, you can do this dynamically within each Jupyter notebook. With Pydap in particular, this is the way you can authenticate. Pydap is also compatible with .NET RC files, so this is beyond the scope of NASA too. You can have login credentials within a .NET RC file, and then Pydap will automatically recover them for you. So in this case, tokens are slightly better, especially when talking directly to Hyrax data server, because it is the Hyrax data server is able to kind of avoid some redirects. Now to the show. So I'm going to demonstrate finding OPeNDAP URLs, constructing the constraint expression interactively so that discards most of the variables that I'm not interested, and then aggregate them really in parallel to create a virtual Xarray dataset object. So if you want to learn more about this project, the Echo Consortium, you can go to some of the references that are pointed in I've potentially here, right here, and then also on the slides, which are findable on the Zenodo or our presentation. So requirements is just to have run that notebook so that the token JSON is stored. You can do this also dynamically the way I showed. And then the objective is, like I said, just to find OPeNDAP Cloud OPeNDAP URLs or Hyrax OPeNDAP URLs in a way that it's potentially hundreds of them, and then just aggregate them. In this case, it's running the latest version of Pydap. Some of these things are kind of new, so I'm not sure how much people are familiarized. How to find Cloud OPeNDAP URLs? Well, you can use a CMR. This is a specific to NASA. A CMR has the common metadata repository with all of the information about lots of the data sets. And in particular, we're going to use the collection concept ID or the dataset DOI, either one of them, along with the time range that you want to subset, essentially. It will be able to parse out information and find all of the relevant URLs. So in this case, it uses a Python request library, which is very performant, and it can also recover credentials on a netrc file. And then here, I already kind of knew what I was going to look for to speed up the process. So I'm going to start the process with looking with the DOI. So here's for this potential collection. That data set has about 10 collections in aggregation. I'm just going to look into that one of them. And so this DOI, essentially what it does is finds a collection concept ID, which I already knew, but I wanted to show anyway. And now this collection covers 1992 to 2018. This is the release 4. I think there's a newer release that covers a little bit of a wider time format. And this data set is actually really nice. It's mostly for oceanographers and climate models, but it covers quite, it's a really interesting data set and data product from NASA. And the way it does is that this little function right here, it's going to be incorporated within Pydap for the next version. But what it does essentially, it just queries the CMR, and it finds, you text as input the concept ID and time range, and it finds all of the information just the way I showed with the browser experience, finding that OPeNDAP URL. It just essentially does the same thing, but in a way that is automatic. So let's see how long it takes. Less than 1 second, and you found 300 URLs. Essentially all of the URLs for this collection. And then here we import the token information and then store it into this session. And this is the part that was actually very interesting. So I'm going to look into one single granule and see what's in there just directly with Pydap, because Pydap is usually faster than Xarray, especially when running just one data set in mind, and to look at all of the metadata. What happened here in 3 seconds is that Pydap talked to Hyrax in the cloud, downloaded metadata, and created the virtual data set representation of what's inside. And you can look at each variable, what's inside, what the name of them, the types, the sizes, and everything. And so you can say that there's a lot of the variables here, and a lot of them are dimensions, a lot of them are coordinates. And I'm not really interested let's say for doing exploratory data analysis, just to see what the data looks like. You probably are not interested in all of this information. So I'm only going to pick 2 variables, salinity and temperature, potential temperature, along with the respective dimensions, because we're going to use Xarray, and Xarray really enforces CF conventions as well. And so it really needs and requires dimensions associated with this data set. And so here, I just printed Pydap is really good for finding the dimensions. They're the same in this case. And this cell right here, it just creates what I called earlier before as the constraint expression, which is essentially this extra bit information that we're going to add to a granule URL. This all can be optimized, by the way, but I'm just showing how to do this in a way that allows you to save a lot of time if you're not interested in all of the data. So I'm going to apply the same thing for all of the URLs. And what I'm going to do is going to tell not Pydap, nor Hyrax, but Xarray that I'm interested in accessing the DAP4. And that it has some connotations that are internal to Xarray that you don't need to know. I do need to know about them. And so essentially what I did is just change the schema of the URL, the granule URL, to say DAP4. You can do the same thing with DAP2, and it would just mean that Xarray is just going to say it's going to be a DAP2 or DAP4 instance. And here is the thing that I'm really excited about. This line that says consolidate metadata. What it does, hopefully my internet is doing well, is that it's going to download all of the metadata for all of those URLs and store them in a persistent object, essentially the DMR pointing to 300 OPeNDAP Hyrax in the cloud URLs. And it did that in 18 seconds and identified the dimensions of all of that data set. And now every time I run this cell, it will take a fraction of that amount of time, no matter how big the data set, 2 seconds, because it's all in cache. And then this essentially what allows is to create a very performant reference to all of these virtually aggregated data set references and points to all of those 300 URLs. At this point, this cell of creating the data set, It's not downloading anything else anymore. It's just doing parallelization to create a dataset object. So in a matter of 10 seconds, I create a virtually aggregate representation of a dataset that points to hundreds, potentially thousands of URLs. And every time I run this ever again, it will be limited by your compute parallelization. And then so no data has been downloaded, and then you can download some data. This is the cube sphere data, so it's a bit complicated topology. But it's only when you hit plot or you do with expert.compute that it actually downloads data. So again, I mentioned earlier before that with OPeNDAP, scientists would have a URL and that we share them. We're changing the paradigm from sharing a single URL to potentially sharing an object that points to a huge collection of URLs. So that's something I'm really excited about. And so some user will have this session send via email or a hard drive, and then they will already point to hundreds, potentially thousands of URLs. The last notebook that I'm going to show is one that is really exciting, the state of the art. And I have to hand it to the people at Earthaccess Virtualizer for this amazing work and essentially writing parsers for DMR-PP. This is a kind of like another way to access data on the cloud. That is, you can run this on an EC2 instance and talking to the data directly on S3. With Pydap, like I said, it talks to Hyrax Data Server directly. The server is the one who's doing the subsetting for you, sends that information, and then Pydap reconstructs everything. So what you'll need for this, if you want to learn more about this Earthaccess, there's some useful references here that I put in this notebook. It's on the binder. This tutorial largely follows that on the documentation for Earthaccess, which I believe it was this by Ayush Nag. If you want to learn more about Ayush's work with writing a virtualizer parser for DMR++, you can go to this reference. And especially if you want to learn about the work that we at OPeNDAP are doing in conjunction with the HDF group, to really allowing this DMR-PP generation for the access, performant access in the cloud, you can go to this reference or to talk to us. So this is the last notebook. Earthaccess has their own way to enabling authentication. It's compatible with .NET RC, so if you have that, that's great. In my case, I don't have it within the binder environment. So what I'm going to do, I'm just going to get my password from my password manager. Oof. And then I'm going to do Earthaccess. And then I'm going to go copy and then just do return, paste it here. And so that should do it. That's all you need to do. Again, in a way that is more persistent, you will have a netrc file somewhere. And so this is going to take a bit of time. What I'm doing here is that, So Earthaccess has this built-in way to search for URLs, or particularly for data sets associated with a temporal time range, short name for the collection, or DOI, the way I showed kind of, because it uses, my understanding, it uses a CMR as well. This is the part that is very interesting. There's two ways to run this. If you're running this on the cloud for future reference, you can set here direct. When I say the cloud, meaning an EC2 instance. In this case, I'm running this on a binder environment, so I'm going to set indirect. And this is actually going to take some time to really use all of the parallelism that is exploited in an EC2 instance on a cloud with Dask. Then you will set this direct. And what it's going to do is it's going to get all of the DMR. It's going to identify it already identified all of these files. It's going to get the DMR++ associated with those files, and then parse them in order to create a virtually aggregate representation of the data set. This is the ultra high resolution sea surface temperature data set from NASA Pydap. It takes about a minute. What is happening here is that it's kind of doing something that Pydap did, which is to download via via internet connection, the DMR++. Now, Pydap only downloaded the DMR. So this takes longer than Pydap using this example, because the DMR++ can be actually much bigger than DMR itself. Again, the ++ part may have all of these references for the chunks that's inside the file itself, and each of them, in case 32. This is a month of data, so you could do that for a full year, which will be essentially 300 and something DMR++. And then so earthaccess with this open virtual MF dataset, what it does is that it gets all of the DMR++ over the network. In this case, you can do it on S3. And then it uses Xarray to create a virtual aggregate representation of that into what will be, the output will be an Xarray dataset. All right, so this is it. You can see that it's a really high resolution. Only 32 files aggregated. Why is this faster than, if the data's in the cloud, why is this good? Well, like I said, mentioned before, is that opening a single file can have a time penalty when you're on the cloud. Just to figure out what the variables are inside, it's much faster to just look at the metadata inside. So I'm gonna run all cells and below. Right, so just as I explained this, so when you have potentially hundreds, potentially thousands of data sets on the cloud, on the particular collection, it's faster via Earthdata to create a virtual representation of with Xarray of that entire collection when it's using DMR++, because the DMR++ has all of the information, again, the mapping of what's inside the file without the client, in this case, earthaccess or Xarray or Virtualizer, which we should mention also. Virtualizer is an amazing package that was developed recently by the ZARP developers. Essentially, it just parses metadata. It's all about metadata, and you don't have to touch a file anymore, at least in this case. So right now, right here, it plotted the file. It's only when I plot the file is that it's actually fetching data. At no point did fetch data until I plot the data itself, or did something like dark compute. So again, it's important to say the distinction of what earthaccess is doing is that it's downloading not just metadata, but the DMR++. And that's can be significantly much larger than DMR. So Pydap sometimes can appear faster in these ways that I showed, but in this case, it's more information and the output may be a little faster when actually processing the information. And so I know that I'm running, I think this is the last notebook. There's some more, this is the more of the experience level that people can do. And again, I encourage users to go to the earthaccess documentation. What it does here is that some really interesting thing is that, again, it's all parsing DMR metadata, DMR++, but you can set it and store it as a chunk object locally somewhere. And that's a really neat feature because it's all metadata that's being moved around. But the metadata points and kind of pre-processed points to data on the cloud. And so no matter where you're running it, that metadata can persist. So you don't have to download it every time. In order to do that, you do have to access it in a way that is indirect and load equals false. And so it's going to take about the same amount of time because it's downloading over the web, 30-something large DMR++. And so it takes about roughly the same amount of time as it did, which is about 1.5 minutes. There it is. And so now you can see the dimensions have not been loaded into memory. And what's interesting thing, one last thing I want to point out is that if you look at the file itself, this is the ++ part of it. This is what's inside: shape, chunks, dtype, field value, order, compression, filters, offset. This is all of the stuff that it's in the DMR++. So what it does then is that it parses information. It turns this chunk references within DMR++ into ZAR metadata via Virtualizer, which is really this amazing thing. And then you can store it as like a chunk and later open it, which is super powerful. One last thing, just to draw a distinction with the, it's going to be less than 1 minute. When running on premises, it's the experience for using earthaccess, or particularly with Pydap in this case, is pretty much the same as before, whether you're running in the cloud or not. This whole workflow is identical to what I showed before. In this case, it's accessing NASA from Pace, this amazing data product from that just launched last year. And it's doing the same thing, finding OPeNDAP URLs really performantly, half a second to find 500 URLs. And then it did something here, which I think is because my internet connection it's dying. It happened earlier today. Let's see if it runs again. And then it's going to take maybe a couple of seconds, and then it should create this consolidated metadata view of this on-premises server, pointing to all of these URLs right here. So it's running fine now. I think for some reason my internet faltered, and 1 more minute and I think I'm done. Opening for questions. Yeah, I think it's something with my internet. Apologize for that. But it's essentially the same workflow as before. And so with that, I'm gonna stop sharing and then open up the last slide for just for questionings, essentially. Let's see.
Okay, well, thank you, Miguel. At this point, what we will do actually is we're going to transition to the final, I'll open up the final optional polls, and then we'll jump straight into the Q&A session. Okay, so let me open those up really quickly.
Okay.
All right. And let me just hold on a second. All right, the poll should be opened. And what I'm actually going to do first, Miguel, is address a question that was posed in the chat early on. Okay, so we'll do that one first. So the question is, do your demos show how to choose a variable and the QC associated with it to download at the same time? I worry that many people might presume that QC is always applied and might not realize that for many data collections, the user needs to apply them to acquire the correct scientific data.
So I didn't repeat the question. I was trying to find it. So it was something about the constraints expressions that.
Sure. Let me read that again. It's in the chat. It's not in the Q&A. So do your demos show how to choose a variable and the QC associated with it to download at the same time? I worry that many people might presume that QC is always applied and might not realize that for many data collections, the user needs to apply them to acquire the correct scientific data.
Yeah, I think I understand a QC constraint. QC.
Well, actually, I was thinking about this, and so I mean the quality control variables are mixed in with the I don't know, the scientific value variables like temperature and salinity and so on. And so really what a person needs to do is go and understand the particular data set and what those variables are called. And the scientific stuff is usually pretty easy to pick out, but the QC stuff can be a little obscure. But it's easy to do what Miguel did and just say, hey, let's have a constraint expression that asks for several variables from this data set at once. And that was, what he showed before when he was getting the salinity and the temperature with the salt and the theta, but you could just as easily include QC information in there as well.
Yeah, thank you, James. And something they mentioned about constraint expressions is that, yeah, when you're using the browser, it's a kind of like a traditional way to construct these expressions to only select what you want. But what things like Pydap or Xarray, what they do really, or some of the backend engines of Xarray that access OPeNDAP data, is that they do also construct the constraint expression for yourself. So when you're using Xarray, talking to an OPeNDAP server, and you just select a subset of the Xarray dataset, and then do plot it. What's happening on the background that you may not be aware as a user is that the backend engine, in some cases, Pydap took that selection from Xarray and it constructs the constraint expression for you, pointing to, so it takes the regional URL for the entire collection of all of them and it applies that constraint expression for you without you even knowing. So that's another way to think about this. And I know it may not be this QC that you're implying. I don't have a lot of experience. I think James was the right person to answer that. But that's just another thing of you can create manually construct expressions to accelerate data it's like OPeNDAP savvy, but you don't need to. If for sure you can just access all of the metadata and then later Pydap or Xarray will construct the constraint expressions for yourself.
Yes, thank you so much. Thanks, James, and thanks also, Miguel. And so if you have posed your question in the chat, if you wouldn't mind adding that question to the Q&A panel, you should see that on the right side of your screen. And if not, you can click on the three dots to pull up your panel options and then insert a check mark next to the Q&A panel. Okay, so the next question, and I think the question is not whether or not data is in the cloud. The question was, in Earthdata Search, how do you know which collections have the cloud OPeNDAP enabled? And I guess I don't think there's any data, is there, that can't be accessed using OPeNDAP? So maybe the question is, well, maybe there might be some, but from other agencies, I'm not sure. So maybe you could weigh in on that. Like, how do you know? I don't think there's any designation saying it's available through OPeNDAP necessarily, but maybe it would be worth showing how to get to those URLs again. Do you know what I mean? Kind of mapping that process. But if I don't have this right, if the user could clarify, that'd be great. So if you're just looking for cloud data, there's, as James stated, there's a designation. You can actually filter by data in the cloud. But let's see if you have additional input that might be useful here for us. I appreciate it.
Yeah, and I think I might have skipped a little bit over it. One thing is cloud data on the cloud, and another thing is data as data OPeNDAP server that is also on the cloud pointing to that data. And so those two are different things that sometimes are overlapping. So earthaccess is a great way to find data on the cloud. Like I said, not all of the NASA data is on the cloud. One way that I showed in this Jupyter notebooks is to overall find OPeNDAP data, OPeNDAP URLs. And then from the URL, you will be able to know whether it's on the cloud or not. That's kind of like a really easy way. If you have a concept collection ID or DOI, one way to also find out if it's on the cloud is with the browser way up approach. I search for a collection. I can show it, but I'm just going to say it. And you're using the search portal, and it will say if it's cloud enabled, Earthdata on the cloud or not. That thing that's the easiest, more straightforward of knowing if that data set's in the cloud, and then you can access it. If you want direct access on S3, you can use earthaccess, or if you want with the DMR++, or if you want to know if there's a cloud OPeNDAP URL, then you can kind of learn what that collection ID is and search for the cloud OPeNDAP URLs, which are going to point to that Hyrax. And like I said in my slides, which are on the website as well, it's going to say opendap.earthdatanasa.gov. If it's something that looks something different, that looks more like a POSIX file system, like in a directory, that's just like traditional on-prem services. And each DAG runs their own instances of OPeNDAP servers. We don't have a lot of control over that. I know that some DAGs are only on premises, OPeNDAP. Yeah.
Well, thank you very much. Thank you very much, Miguel. So let's see here. There was another question asked in the chat, and then I'm going to focus on those questions that are in the... If you could kindly place your questions in the Q&A panel, that would be very, very helpful. I really appreciate it. So the next question is, does the OPeNDAP access to the cloud work with MATLAB? And do you have plans to develop techniques for MATLAB?
Yeah, that's a really good question. We focus a lot on Python, and for sure I know that you can access OPeNDAP data with MATLAB. The fact that you can just get to that data request form of OPeNDAP on the cloud, which will look like opendap.earthdata.nasa, MATLAB has support for opening data sets with URLs like that. And so as long as that exists, you should be able to open it. I'm not sure how performant it is because it's using Hyrax in the cloud. It will use DMR++ via Hyrax. So you can think of it as a way to provide backward compatibility with all these other clients. I will work to provide some examples. That's a really good suggestion, to provide some examples for accessing this data with MATLAB, which is used widely. I mean, I'm from Mexico, and I know that a lot of my friends in Mexico are still using MATLAB, which is great.
Okay, thank you so much, Miguel. Let me get back to the Q&A. Thanks for your patience, everybody, as I get to the next question. So the next question is, how can I control the timeout when using Pydap and Xarray? It seems to happen arbitrarily. For the same data size, it might it might sometimes give timed out error while other times working?
Yeah, that's a good question. I've run into some of that very infrequently. You can specify the timeout. I think the default timeout for that is 512 seconds, but you can pass an argument. You can go to Pydap's documentation, and there's an example there. I'm maintaining the documentation, and I'm improving it. It's been updated recently. It hadn't been updated in many years, and so I did provide an example of how to control the timeout for that session. Yeah, that's a good one. Very specific. Yeah, thank you for that.
Well, thank you so much. Let's see here. I did see there was one more question in the chat, and let me see if it's been asked. Okay, good. So let's go ahead and continue forward here. Well, thank you too for adding some additional feedback on that last question, James. Really appreciate that. Okay, so the next question is, will Hyrax be able to serve virtual data cubes in the near future? For example, consolidated DMR++, or even ZAR-like per chunk?
That's a great question, James. You want to address that one?
I said, yeah, that's a great question. Talk to us. Conceptually, yes, absolutely. We can serve data. We will be able to serve things from the data cube. But I think the real issue is, have we worked on it? And the answer is no, we haven't gotten there yet. So, but we're really interested in that. And of course, data cubes have been on people's radars for a long time now. And in fact, the kinds of virtual aggregations that Miguel showed are a kind of data cube, right? But that might not, but you might have something much more specific in mind, Lewis. So yeah, you should definitely get in touch with us.
Okay, thank you so much, Miguel and James. The next question is, I'm trying to figure out the differences between using Pydap or the DMR EP files and creating a virtual, I think this is meant to be DMR++ files, and creating a virtual reference file using e.g. virtualizar. Happy to clarify this more.
Yeah, so that was a question to clarify, or
I guess kind of restate the differences between, if I don't have this right, Dean, let me know, between using Pydap or the DMR++ files and creating a virtual reference file using virtualizar.
Oh yeah.
I think I've got that right, Dean, but if not, please do add something into the Q&A.
Yeah, and I can just clarify that when you're using Pydap directly, it's talking to the server directly. The server is the one that constructs its DMR representation on the cloud on the fly, I believe. And so it's really not touching the DMR++ directly. It's the server it's the server acting kind of like a client itself. Is parsing, is getting a request from a user, and it's figuring out what bits of information and where that information lives when you're using Pydap. So it's through the server directly, and then the server sends a DAP response, which is binary, and Pydap reconstructs that as a NumPy array. So that's all happening really fast, and it's really streamable response, as opposed to download it as an etcd4, which is the traditional approach, and etcd4s are not streamable. So with DAP response, that's really fast. When using earthaccess with virtualizar to just talk directly to the DMR++, you're just kind of like avoiding talking to Hyrax directly. And I think that that's when running in the cloud, that gives you a huge performance boost, because now it's the virtualizar and earthaccess what is doing the work of the Hyrax data server, even though they're both talking to the same metadata file directly here. To talk to the same file, they're just following different routes to how to do it. And one of which is a very interesting idea of two ways of approaching the same thing, just two different ways. And one of the things I've talked briefly with the earthaccess guys, it will be really interesting to benchmark talking and then downloading data with Pydap, for example, a subset, and then downloading the same data with earthaccess, talking directly to the to the DMR++. My guess is that it will probably be more performant, DMR++, but I actually don't know. It was kind of interesting because they're two slightly parallel approaches. Yeah.
Okay, and is going to be, all right, Roy, would be nice if DMR++ can be made independent of Hyrax so other things can use that to read and write existing data sets to the cloud and be performant. And that way they don't need to be reformatted to ZAR.
That is a really good point. I saw that, Roy. Thank you for that. In many ways, one can run Hyrax. I know it's still dependent on Hyrax, but you can just run it to construct the DMR++ and just make those available and move them around. But yeah, it's a very interesting idea. What do you think about that, James?
Well, yeah, definitely. So there's a couple of angles on that. Exactly what Miguel just said. In fact, ironically, I have just to my left here, out of view, a draft of the document that describes how to build DMR++s using a Docker container that we provide. And that's actually the Docker container that NASA uses when it builds the DMR++s in its Cumulus task, which is how the INA train onboards data. So there's that. And then, of course, there's the DMR++ parser that Ayush Nag wrote when he was doing the initial virtually ZAR work. So there's already some software out there in the world that can work with DMR++s, both producing and consuming. And that's definitely something that we would like to see much more of. One of the things that we haven't sort of talked about here is the complexity of the NASA data system, which is just shockingly complicated. And so there are a large number of collections, and in some sense, they're standardized on HDF4 and HDF5. But when you look under the hood, neither HDF4 nor HDF5 are really a format. They're really a representation for a potentially extremely large number of different formats. So we've been working, OPeNDAP has been working under contract with NASA to expand the coverage of all of those different collections so that valid DMR++s get produced for them. And so there's actually so the DMR++ document effectively becomes a state document about the organization of a particular granule. So anyways, that's kind of a long-winded answer, but I think that's all I'll say for right now.
All right. Well, thank you so much. All right. So let me go down here. The follow-up from Dean is, maybe this is covered. So getting back to the question. So to clarify, they are not duplicating efforts.
Oh, you mean like the Pydap and virtually ZAR?
Yep.
Right. Yes, as Miguel said, they're really fundamentally two different software architectures. In Pydap, you've got a client and it's talking to a data server, sending it information and asking that data server to provide some assembly operation and then sending the assembled data back. With virtually ZAR, what you're doing is you're saying, okay, I know you have these state documents about the organization of the data files. Bring all of those state documents to me and I will assemble them, and then I will perform the data assembly locally. And this is fundamentally this second architecture has emerged in the last, say, decade with the emergence of cloud data systems. And part of the reason that that's happened is that web object stores, of which S3 is one example, support a high degree of horizontal scalability. So they can accept a large number of parallel accesses, whereas a regular web server, and I know it's really weird when I go like this, but anyways, I'm sorry, it's a personal habit. Web servers generally are limited to a relatively small finite number of parallel accesses. And so they like to do their work all internally. Does that answer your question? All right. Cool.
Yeah, so for security, participants are muted by default in the WebEx, not the WebEx webinars application. And sorry I didn't catch the chat quickly enough,
That's okay.
but because I was looking at the Q&A. However, let's move on to the next. All right. See, I think. All right. So does the OPeNDAP cloud provide a way or URL to browse all the granules in a collection? I know that the CMR virtual directory, but it is slow and frequently returns errors.
Right. So that's an issue that I'll just jump right in on. That's an issue, and we don't really directly control the CMR virtual directory software. You know, the development team for all the NASA cloud work is quite large, but we are aware of the issue and we're looking into it. And it's great that we've got some feedback. So thanks very much. And I'm sorry that it's not fast and sometimes returns errors.
Okay, well, thank you so much, James. Let me see here. And then just as a follow-up to an earlier question that I asked, hi, James. Clearly, I'm also thinking of Pydap. We want to interact with Hyrax. We also want to be able to use this to if we move some of our files to the cloud and we are interested in Java for obvious reasons.
Right.
I had intended to read that a bit earlier, but just as a follow-up, I wanted to make sure that I conveyed this information.
Right. Yeah, no problem. Well, that's great because I'm a big supporter of the Pydap server and all the things it's done. I've noticed its growth, and I think that's great. And so we would love for you guys to be able to use DMR++ in your work. And we don't have a Java parser yet, but we do have a C++ parser and a Python parser. So I imagine that a Java parser is pretty doable.
Okay, well, wonderful. Thank you so much again, James. So the next question is it's really more of a, so there's a follow-up on the previous answer. Does it mean virtual czar versus Pydap can give faster and more secure access to larger data sets?
I don't really.
Question. That's we don't know. Yeah.
Yeah, I mean, there's a lot going on in there. And I think if you were to talk to Ryan and Joe, Ryan Abernathy and Joe Ham at Earthmover, you'd probably get the same, yeah, we don't really know. But they're also working on similar ideas.
Yeah, and I want to also just mention that this is kind of like ongoing efforts that I'm talking to the earthaccess guys because we're kind of interested in benchmarking this. This is all new stuff that we're all excited about, and so I see that Luis is here. So it's this is something that we talked about last week about inspecting this behavior and performance because I don't really know either.
Right.
Good question.
Component, and we'll leave the virtual meeting space open an additional 10 minutes or so. So if our panelists could stay on the line for an additional 10 minutes, that would be wonderful. So with that, what I'd like to do is to thank everybody, all of our participants for joining us this afternoon, and to thank our speaker, Miguel, and also to thank our Q&A panelist, James, and my backup host or co-host, Joseph Smith, for his assistance this afternoon. And so with that, I wish you all a wonderful rest of your morning, afternoon, or evening. And we hope to see you at an upcoming webinar. All right, everybody. Thanks so much. Goodbye.
Thank you very much.